Like. Yeah. Subscribe.
Hey y'all, welcome to Precalculus. This semester, we're going to primarily focus on learning trigonometry, but before we get into all that, we're going to review some key concepts from your algebra classes from yesteryear. Hopefully these will help you be more successful as we go through the year, because these solving techniques that we're going to go over the next couple days are going to be used throughout the whole year. So let's go ahead and get started. Now, you can read all this. You don't need me to read this. Basically just explaining what an equation is. What we want to focus on is how to solve equations. In other words, how to find the value that will make the equation true. So let's look at some real basic examples. Notice these are all linear equations. You can see really quickly they're all going to be one-step equations. And what we're going to do here is utilize the properties of equality that we have to isolate the variable. So what I mean is we want to get this variable, this x, all by itself. And to do that, we need to sort of shift things around. We need to get everything away from this side of the equation, with our ultimate goal here being x equals some number. So that if we can get it down to this using our properties of equality and some other properties we'll look at in a minute, then we'll be in good shape. So to do that, like I said, we're going to use the properties of equality, which essentially say if you do something to one side of the equation, you're allowed to do that as long as you do it to the other. And specifically, what we want to do is we want to undo what is being done to the variable. So we'll use the opposite or the inverse operation to what's being done to x. So here we've got x plus 4. So to undo that, we are going to subtract 4 from both sides. And the way I like to show this work is just to write the expression right below the step, whatever we had previously. So basically you just kind of line up our like terms here. So we've got x plus 4 minus 4, and we've got negative 12 minus 4. And we can kind of collapse that down to just a single equation. This shouldn't be really a big surprise to anybody what's going to happen here. So 4 minus 4 is going to be 0, and then negative 12 minus 4 will be negative 16, and that's going to result in x equals negative 16. Now y'all are going to have to forgive me here. It's been a whole summer since I've recorded one of these videos, so just bear with me here. For this next one, we're going to have to add 6 to both sides. None of this should be very revelatory to you. You've been solving problems like this since, gosh, probably at least 4 years ago, I would say. So, you know, this should really be pretty basic. We're going to add 6 to both sides. Just trying to clean this up a little bit. And then, so we should get x equals 1. So I just want to point out here that, you know, obviously addition's the opposite of subtraction and subtraction's the opposite of addition. So if you're trying to undo subtraction, you're going to add that number to both sides. If you're trying to undo addition, you subtract on both sides. The same general concept is going to hold true for multiplication and division. So when you multiply a variable by something, if you want to undo that for the purposes of isolating the variable, you're going to divide both sides by that same number. So like in here, in this case, I'm going to just I'm going to use a fraction bar to notate division here. I'm not going to use the division symbol. Instead, let's go ahead and write it like that. So I'm going to show that I'm dividing both sides by 10 here by essentially creating a fraction. As long as I divide both sides by 10, I should be safe. So I'm going to divide both sides by 10, and 10 divided by 10 is 1, and that's kind of what I want to happen. Is I want for that 10 to kind of disappear, go away. So what I'm left with here is n equals 4. For this next one, we've got k divided by 11 equals 6. And to undo that division, if you've been paying attention, you probably already know what's going to happen. We want to multiply both sides by 11. Now, there's a couple different ways you could show that, and it's really preference. I don't really care which way you do it, One way you can show the multiplication on both sides by 11 here is to write it like this. You want to write times 11. Now, I'm not sure if, let's see if Cami has the dot in there yet. If not, we can pull it up elsewhere. Let's see what we got, what we're working with here. I do not see a dot here. I think I'll just steal it from online. Here we go. So, in other words, you can kind of write it like this where you're showing the multiplication on the other side. I'm not too crazy about this because it's sort of different than all the other ones. It's fine if you want to write it like this. I'll usually write like the times 11 below. That's just me though. It's up to you. It's just sort of personal preference on how you want this to look. So anyway, we're going to multiply both sides by 11. So anyway, we've got, we're going to multiply both sides by 11 here. And we're going to get k equals 66. All right, so what we've shown here are just the 4 properties of equality. Essentially, all you really need to know from here is that if you're trying to undo an operation to a variable in an effort to isolate the variable, just do the opposite. And you must do it to both sides. That's kind of the key thing. Is whatever you do to one side of an equation, you have to do it to the other so the equation stays balanced out. But as you could probably guess, our equations are not going to be this simple. We'll definitely have multiple steps in all the equations that you're going to have to solve, like for homework and quizzes and things like that. If you have multiple steps to do, like let's say you had something like 2x plus 4 equals negative 12, like up here, you'd want to undo the addition and subtraction before the multiplication and division. So we'll have some examples where I'll get to show that, but just a little heads up there. Now there's there's really 2 other things we need to talk about in terms of linear equations. The first thing is this whole idea of combining like terms and dealing with equations that have variables on both sides. So in general, you want to try to simplify each side of the equation first, as you do as much as you can in terms of combining like terms. And what I mean by that is to add your terms that have an x and combine the terms that don't. So if you've got well, let's just go straight to the examples here. Notice in this first equation, on the left-hand side, I've got 2 like terms. In other words, I've got 2 terms that both have an x. So I want to try to combine those. Now you'll notice that you also have an x term on the right-hand side of the equation. We're not going to deal with that up front, okay? We'll wait until we've got both sides of the equation simplified, and then I'll show you what to do when you have a variable on the other side of the equation. So first things first, we're going to combine these 2, and that means you just add them together or subtract them if it's subtraction. So we want to combine an 8x with a negative 3x. So 8, 2 ways to think about it, either 8 plus negative 3 or 8 minus 3. Either way, you're going to end up with 5x. Oh, capital X there. Not sure what happened there. So we got 5x, and then this plus 5, nothing's really going on with that. And then we've got equals 8x minus 4. So the first thing to do is to combine your like terms, and then you have to worry about the fact that you've got x's on either side. So this is still kind of like combining like terms, but we're going to use the properties of equality to simplify this equation further. So basically what you want to do is you want to try to collect all of the terms that have x on the left-hand side and all the terms that don't have x on the right-hand side. And technically it doesn't really matter what's on the left and what's on the right. You just want to sort of separate the different terms. So in other words, collect all the x terms on one side and the non-x terms on another. I just typically will collect the x's to the left out of habit so that my final answer can be x equals instead of having to switch it around at the end. So to use these properties of equality, basically what we want to do is we want to get rid of the 8x on this side. We want to sort of move that over here and collect it with the 5x. And then we're going to move the 5 over. Now, as we saw previously, you can't just sort of move things around. You have to use those properties of equality. So I'm going to actually knock out both steps here in one. So like I want to move this plus 5 over here. So I'm going to say minus 5 on both sides. I'm just picking a different color just to really sort of show that I'm doing, what's going on here? There we go, minus 5. Okay, so I'm going to subtract 5 on both sides here. But I'm also, what that will do is that'll cancel this out, and then I'll basically collect it over on the right-hand side. But since I'm, in pre-calculus now, I'm not in Algebra 1, I feel comfortable getting rid of this 8x and moving it over here within the same step. So I'm going to actually subtract 8x as well. And I'll subtract 8x from over here too. So notice I am doing the same thing to both sides. I'm subtracting an 8x from both sides. I'm subtracting a 5 from both sides. I'm doing that to cancel out the 5 over here and to cancel out the 8x over here. So let's go ahead and combine all that stuff. So we've got 5x minus 8x is going to be negative 3x. Let's go back to red here. Then we have 5 minus 5, which is 0. Those cancel out, which is what we want to happen. The whole purpose of moving these things around is so that we get our constants on one side and our linear terms on the other. So over here we've got 8x minus 8x, that's 0 again, that's what we want to happen. Right, so we got these to cancel out, we got these to cancel out. And then we got negative 4 minus 5, should be negative 9. And so now we've got a one-step equation like we had up here, where we just had to do a single operation to undo whatever's being done to x. Here we've got negative 3 times x. So for multiplying, we want to do the opposite, which is going to be to divide. And we're going to divide negative 3 on both sides. Negative 9 divided by negative 3 is going to be positive 3. So we get our solution, x equals 3. Now it's usually a good idea to go back and check your answers. I kind of neglected to do that on the last few, but really what you want to do is you want to go back and plug this into the equation to verify that it does in fact work. So I'll do that for this one, just so you can kind of see how I would do that, but I'm going to kind of skip the rest for the sake of time. So let me pull up my calculator here. This is where, if you're just checking to do a quick check, calculator is kind of the way to go here. So we've got 8 times 3. I'm just going to retype the entire first side of the equation, but instead of x, I'm going to substitute in the 3. So minus 3 times 3. Just a parenthesis there. Okay, so that's the left side of the equation. What we want to try to check is to see that the left side of the equation is the same as the right side of the equation. So we got 20 on the left, and on the right we got 8 times 3 minus 4 is also 20. So x equals 3 checks out, and we're good. Like I said, I'm not going to show you every single one of these. You don't need to sit through that. But as you're working through your problems, it doesn't take but like 10 seconds to plug it in just to make sure you get the right answer. Let's do one more here. So for this next one, again, we've got some like terms. We've got the x's that we want to combine. Oops. So we've got single x plus 7x is going to be an 8x. And it doesn't look like we have any other like terms, so we're just going to go with 8x minus 10 equals 15 plus 3x. Now we're going to do this step right here where we start collecting variables, or terms rather. And what I'm actually going to do is save myself a little bit of typing, or not so much typing, but formatting, is just copy that whole thing and let's just change it to what we want it to be. So instead of subtracting this minus 10 here, we want to add 10 to both sides. Ooh, there we go. And then instead of, let's see, we want to move this 3x over to the left-hand side, so we want to subtract 3x from both sides. Okay, so put a little space in here just to make it obvious that we're not just, let's see, I think that looks pretty good. Let's line this up a little better. Yeah, that looks great. Okay, so now let's combine our like terms. Combine these columns. 8x minus 3x is going to be 5x. Negative 10 plus 10 is going to be 0, which is what we wanted to happen. We wanted to get rid of the constants on the left-hand side, and just like we want to get rid of the linear terms on the right-hand side. So these linear terms over here will cancel out. We get 15 plus 10 is going to be 25. Here, we'll divide both sides by 5. Ooh, font changed on me. You know what, I'm using text instead. That's fine. Don't want to get hung up on that. So we're going to divide both sides by 5, and 25 divided by 5 is 5. So it's one little extra layer of complexity to these linear equations is if you've got multiple variables, you want to know, really what I want to emphasize here is if the like terms are on the same side of the equation, like we saw in this first step, you want to collect those together by just combining like terms like you normally would. But if the like terms are not on the same side of the equation, if they're on different sides, you need to use the properties of quality to move that term over. So in other words, you need to subtract it or add it or do whatever the opposite is for the sign on that term. Okay, so that deals with all the variable issues. There's one last little layer of complexity that we might see on these linear equations. And that is how to deal with parentheses, okay? And to do that, we essentially use what we call the distributive property. Now, what I'm going to show you is that you can use the distributive property, but you can kind of also get around not using it. And depending on what's going on with your equation, you might use one strategy versus the other. It kind of just depends how the equation's set up, and I'll explain to you. In some cases, it won't really matter which way you do it. And so let me show you real quick what I mean by this. So as you know, the distributive property tells you how to deal with a combination of multiplication and addition. So in other words, if I multiply a term by a sum of terms, I can just add up the product of, in this case, a times b and a times c. So I distribute that term that's on the outside of the parentheses, the one that's being multiplied, into each term on the inside. And so in general, what we say is if we have a times b plus c, that is equivalent to saying a times b plus a times c. Okay, and that is the distributive property. So we can use the distributive property directly here, down here, but we can also kind of solve this equation a little differently, and I'll show you how, and then we can talk about why you may or may not want to do one way or the other. So if we just do a direct application of the distributive property here, we're going to multiply this negative 2 by both of these, and that'll give me negative 8x plus 6 equals 30. So notice I multiplied both terms by this negative 2, making sure that I'm multiplying by a negative here, and that's going to flip the signs of both of these terms. And then I just solve it like a two-step equation. Okay, so like I want to subtract 6 from both sides. Then I'm going to divide both sides by negative 8, will be my next step. So here we go. We're going to subtract 6 from both sides. That will result in negative 8x equals 24. Then I want to divide both sides by negative 8. Hopefully as the year goes on, I'll get a little faster at this, y'all. There's got to be a quicker way to do this. Okay, so dividing both sides by negative 8 here will result in x equals negative 3. So we get the solution here, no problem. This is just a direct application of the distributive property. Now, I did want to bring up that if you can, especially if there's no variable on this term, this sort of a term up here, then instead of distributing, you can divide both sides by that factor. So we can divide both sides by negative 2 here. And in this case, it doesn't really save any steps necessarily. So this is a case where I don't think it really matters whether or not you do this. If you work it this way versus working it the way I'm about to show you, I'm not sure that you're really saving any steps or anything, but there may be cases where this will kind of make your problem a little easier, and we'll talk about that as soon as we're done solving this. So dividing both sides by -2 is going to give me 4x minus 3. I'm stuck on the text again. 4x minus 3 equals -15. I think it is actually the exact same number of steps if you count the application of the distributive property as step. Here, now we've got our two-step equation. So we're going to add 3 to both sides. And then finally, we'll divide by 4, and we should get the same thing. And it does look like we are going to get the same one. So we get x equals -3. Okay, so let's just talk briefly about why you would do one way versus the other. Okay, now if instead of doing the distributive property, if you've got if this distribution is going to make these numbers big, and let's say we're not solving a linear equation, but let's say it's maybe quadratic or logarithmic or some kind of other kind of equation that maybe is a little bit more complicated, it may be wise to go ahead and divide both sides by -2 up front, like we did over here. If it's just real basic like this, you can see it doesn't really matter. But I think, in the overall scheme of things, in general, and again, there's always corner cases and cases where this isn't going to be true, but in general, I do like dividing both sides just because it makes your numbers smaller and easier to work with mentally. If you're trying to avoid using a calculator, it's just a little easier to say divide by 4 than it is to divide by 8. And notice your numbers are smaller here. So if you're trying to solve this without a calculator, probably best to divide this out. But if you're using a calculator, then I guess it doesn't really make a difference. Now, if this division is going to end up giving you some fractions or decimals, then it's probably not even worth it. So if this was let's say a 7, and we had to do 30 divided by 7, okay, well now we've got a fraction here, and I don't really want to work with that. So it just kind of depends on what's going on. I just wanted to show you that there were 2 different ways on how you could sort of deal with this situation of having a number in front of the parentheses like that. So let's just work out a couple of examples here. We've got, they both look kind of long, and they've got kind of a lot going on here. In terms of the order of the steps here, I like to do the distributive property first, followed by combining like terms, and then we'll collect our terms, and then we'll do our 2 steps where we do addition, subtraction, multiplication, division last. So we'll start by using the distributive property. And what I'm going to do is I'm actually going to work out both of these problems simultaneously so you can kind of see that the steps are the same regardless of, these equations look totally different. But when you really start breaking it down, you're just doing the same thing. So what I'm going to do is just start with any distributive properties that I see. Here, it doesn't look like, dividing everything by -3 is really going to be a great plan because we're going to have to divide every single term by -3. So, this little strategy here, not really going to be helpful. Same kind of deal over here. I could divide both sides by -2, but then that's just giving me another fraction here. There's no advantage to doing it that way for either of these 2 problems. So that's going to give me -3x minus 12 plus 1 equals 3x plus x minus 4. Now you might be tempted to go ahead and start combining like terms on the previous step, but I would really recommend keeping those steps separate. If you've got multiple distributive properties or multiple combining like terms, yeah, feel free to go ahead and do those on the same step. But if you're doing 2 different, using 2 different properties, best to avoid not doing them on the same step. It will make your work cleaner, and it'll make it less likely that you make an error. Over here, we're going to distribute the 2/3. So 2/3 times 3 is just 2. So that's going to be 2x, and then 2/3 times 9 is 6. So we get 2x plus 6 equals negative 4x minus 12. The next step, which I'm not going to have to do over here, is combining like terms. So in this first one, I've got this negative 12 plus 1. Those are like terms. Over here, I've got the 3x plus x. So notice, like, it doesn't, you know, when I say combine like terms, you're not just looking for the terms with x's. If you've got multiple constants on a single side, you can combine those as well. And we want to get it into basically like a form like this, where you just have a single linear term, a single constant term on either side, at the very most. And then we'll start moving things around. So combining these, I get negative 3x minus 11 equals 4x minus 4. Here, I'm not going to do anything because I didn't really do this step over here. So I think what I'll do is just kind of shift this down a little bit because I didn't really need that step. So now is where I'm going to I'm going to switch colors here. See if we can find, maybe I'll do blue. Because I just really don't want this step to kind of get lost. I did it in purple before. You don't want it to look like, you know, like that you've done anything. We want to make it clear that we're actually doing the step. So anyway, here we're going to add 11 to both sides. So we'll start with that. But we also want to move this 4x over to the left, so we're going to subtract 4x from both sides. All right, so we got the negative 3x minus 4x is going to be a negative 7x. Negative 11 plus 11 is 0, which is intentional. We wanted that to zero out, just like we wanted this to zero out. We got negative 4 plus 11 is going to be 7. Oh, okay, good. I was a little worried that was going to turn into a fraction, and not that it would make that big a difference, but it doesn't, so we are good. Okay, well, actually, before I do the next thing, let's go ahead and do the same step over here. So here we want to add 4x to both sides. It's gonna let me, oh, there we go. Oh no, I did not like that. All right, work with me here, Cami. There we go. Okay, so plus 4x, and then let's see, we're going to subtract 6 on both sides. So nothing really different than what we did over here. We're just moving our x term to the left and moving our constant to the right. So that'll leave us with 6x. Ooh, keep accidentally clicking on the text rather than the equation. 6x equals negative 18. So next step is going to be the same on both of these. We're going to divide both sides by the coefficient of x. On the first problem, that number is going to be a negative 7. And on the second problem, it will be 6. And we're pretty much done here, okay? So 7 divided by negative 7 is going to be negative 1. And then negative 18 divided by 6 is going to be negative 3. A lot of negatives. Okay, so these are the kinds of equations you're going to see most likely in terms of linear equations, you know, ones where you have to do all the steps. So just to kind of refresh here, you want to use the distributive property first, combine like terms, like we did here, then move your linear terms to the left and your constants to the right. Then at that point, actually, if you've done all of that, then the last step should just be to divide in both cases. Okay, so that's it. There are a couple of special cases, like kind of weird things that can happen when you're solving these equations. And then we'll briefly go over how to solve equations that are quadratic in addition to ones that are linear. So there are essentially two special cases, and that is because it is possible for there to be no solution to an equation. So for instance, like if I have x equals x plus 1, there's no number that I could plug in here that would make it true. Like just pick any number, like 5, and you can see pretty quickly why that would never work. 5 equals 5 plus 1. Well, 5 does not equal 6, right? So anytime you would say like something equals a number that is one more than that number, that's never going to be true, right? If you were to work this out algebraically, what you would do is subtract both sides by x to try to collect the terms. Like if you're just going through the, the normal solving process, if you were to subtract x on both sides, you're going to be left with 0 equals 1, which is obviously not true. Okay, it's a false statement to say that 0 equals 1. And then so anytime if you're left with a false statement, that means that there's going to be no solution to the equation. So let's say you're solving and you get something like 10 equals 15. That's false. So you would say there is no real solution. In fact, here there'd be no solution. Not even let's just say no solution for now. When we get to quadratics, there may be possible that there is a solution that's not real. So we'll get to there when we get there. So for right now, I'll just say no solution. So, I call this a special case because it's not going to pop up that often, but it is possible for you to solve an equation, or at least try to solve an equation, to where there's just no answer, that no number is going to make it true. Now, what about an equation like x equals x, right? Like let's say I tried to plug in 4. Well, 4 equals 4. Yeah. If I substitute 10, 10 equals 10, and so forth. So here you can see it doesn't really matter what x is. This is always going to be true, okay? In a case where it's always true, you're going to say that x could be any real number, okay? We're going to say real numbers for now, although it's possible. We just have not talked about numbers that are not real yet, so I don't really want to get into that. So for now, we'll just say that all real numbers are going to be solutions. Now, if you're working this out, using those properties of equality, you're going to end up with a statement that is just always true. When all the variables cancel out, you'll either be left with a false statement or a true statement. Okay, 0 equals 1 is false, obviously, and 0 equals true is 0 equals 0 is obviously true. So what I want you to say or to give as your solution is to say that x could be any real number. So you can just like spell that out, or you can get kind of fancy with it and say that x is an element of the set. Do we not have that? I'm going to have to go find that symbol real quick. Give me just a sec. So x is an element of the real numbers set. So let's see, do we have that either? Nope. Let me just draw it out. I'm not sure if I'm going to find that really easy. So the way to draw the real number set is you do 2 vertical lines, and then you basically just make an R. Okay? So if you just want to say all real numbers, that's fine too. That's kind of a lazy way to do it. But if you want to if you want to look fancy, this is kind of the way to say it. In other words, the point is that x could be any real number, and this equation would be true. So there's infinitely many solutions. Make a little note about that. All real numbers. You can say something like infinitely many solutions, et cetera, et cetera. There's many ways you can sort of state the same thing, get the same idea across. Okay, so those are the special cases. We've got one last thing to go through, and that is how to solve a quadratic equation. Okay. Now, the steps that we used for linear equations are not always going to work for quadratic equations. In some cases, they will. But if you have an equation that has both a squared term and a not squared term, so a quadratic term and a linear term, then those properties of equality are not really going to work for you. You can move these around all day, but since these are not like terms, you're going to be stuck with these two separate terms, and you won't be able to isolate the x like you would in a linear equation. So instead, you have to use some other method. And when you were in Algebra 1, and then you probably reviewed it in Algebra 2, you learned several methods for solving quadratic equations. Specifically, you might remember the quadratic formula. You might remember factoring. You might remember trying to solve by graphing, where you pick out the x-intercepts. We're going to focus on factoring, and the reason for that is for next year when you get to calculus, primarily the only factoring that you need to do, the only solving you need to do for quadratic equations, most of the equations are going to be factorable, and they're going to be pretty easy to factor. So I just want you to be, just kind of remember how to factor. We're going to do some easy ones. We're not going to make them super complicated. But I want you to sort of get in the habit of trying to solve these quadratics by factoring, so you don't forget that factoring process. So let me kind of break down how you do that. The first thing you want to do is you want to set the equation equal to 0. Oh, wow. Need some typing lessons. Okay, so first set it equal to 0. And yeah, I mean, we do use the properties of equality to do that. In other words, you just want to move everything to one side. So we're going to add 12 to both sides. And that should result in, let's get this set up. There we go. 2x squared. Oh, that's a text. We don't want text. 2x squared plus 10x plus 12. Then you want to find out if there's anything you can factor out. Okay, you want to look for a GCF. Now, you won't always have one, but if there is one, you always want to look for that first, just because it will make your factoring process go a little bit easier if you factor out as much as you can. So factor out the GCF. Now, if that GCF happens to be a constant, like in this case, our GCF is 2, there we go. If our GCF is a constant, we can divide both sides by 2, which is kind of what we're going to end up doing here. Going back to our distributive property, we're going to use this technique on the right. Because otherwise, if we just distribute it back in, then it sort of undoes. The whole point of taking the GCF out is so that we can get rid of it. So anyway, let's go ahead and factor out that GCF. And so we'll have 2 times x squared plus 5x plus 6 equals 0. Now, from here, we want to divide both sides by 2 to get rid of that 2. And the reason why that's kind of nice to do it that way is if we divide both sides by 2, 0 divided by 2 is just 0. So we get a much simpler equation to work with here, which is just x squared plus 5x plus 6 equals 0. And so this is where the factoring comes into play. Okay, so now we're going to factor the remaining polynomial. Now, when you're factoring quadratic like this, you may have learned different techniques like factoring by grouping is a real popular one. I really want you to get to a point where you don't have to do that, where you can just know that, hey, I know I'm going to have two parentheses, it's going to equal 0, and what I need to do is figure out what's in those parentheses. Now, if there's no GCF, finding the first term in each binomial should be pretty easy. It's just going to be x times x. Well, let's, I don't know why I keep clicking on the text over there. So we know it's going to be x, and it's going to be plus something, and then x plus something. Now what you're looking for is, these first two terms, like the x and the x, they have to multiply to give you whatever this first term is. Okay, this is the first. Okay, you might have heard of FOIL before, right? First, outside, inside, last. This is the f in FOIL, right? So x times x has got to be x squared. And then to figure out what these other two numbers are, I'm assuming plus because both of these are positive, but these could be minus if one of these numbers is negative. How do I go back and, oh, there we go. Talking out loud here. All right, always gets me in trouble. So what we want to look for the numbers to go here and here are going to be two numbers that multiply to give you this number, but add up to give you this. Okay, so two numbers that multiply to give you 6, but add up to give you 5. So let me make a little note on that. So let's see here. I don't want to state this. Find two numbers that multiply, or I think I can word this a little better, whose product is 6 and whose sum is 5. Okay? So now these are just the numbers from this particular problem. If you're factoring a different problem, obviously you want to change these to be whatever that is. So in other words, like the c value and the b value, if you think of this as like ax squared plus bx plus c. Either way, we're going to get 2 and 3, and it doesn't really matter which order you do it in, but 2 times 3 is 6, 2 plus 3 is 5, so we've got this factored. This should be pretty quick, okay? Now if these numbers are big and have a lot of factors, it might take a little bit more time to kind of figure out what the combination is, especially when you start throwing in negatives. But the more you do it, the better you'll get, and the more natural they'll come. Now, once we get it factored like this, we are going to use the zero product property. What the zero product property says is that if I am multiplying two things and the product is 0, then one of these things has got to be 0. The only way a product can be 0 is if at least one of the factors is 0. So just think about it. Like, can you multiply two numbers and the product is 0 if neither one of those numbers is 0? Of course, that doesn't work. So because we know at least one of these has got to be 0, we can assume that any value that makes this equal to 0 and any value that makes this equal to 0 will make the entire equation equal to 0 and will be a solution to our equation. So we're going to basically split this up now into two separate statements. Either x plus 2 could be 0, or x plus 3 could be 0. Now once you split that up, now we're just dealing with linear equations like we did before, and you could just use those properties of equalities, use those inverse operations to solve. If we subtract 2 from both sides here, we get x equals -2, or we get x equals -3. So we get two solutions here for a quadratic, and that will be the maximum number of unique solutions you will get in a quadratic is 2. In fact, you will always get sort of two value. Well, I don't want to say anything that I'm going to have to really clarify there. Basically, we'll just leave it at the maximum number of unique solutions you can get to a quadratic is 2. It will not get more than that. What's going on here? I don't know why I got off of this earlier. Where's red? Come on. That's not the same red. Is it that one? That's fine. Okay. Oh, I lost one of my ors somehow. Okay, there we go. Okay, so yeah, basically I get two solutions here. In other words, if I plug in -2 into x here and here, this thing should equal -12. Same thing if I plug in -3, it should also equal -12. So you can expect usually to get two solutions, although you might get one repeated solution. You may also get that there are no real solutions here, to where there's no real number that you could plug in to make it true. So that could happen as well. But for right now, let's just focus on ones that you can actually factor. So let's just try a couple of examples real quick, and we'll be done. I know I've been going on for a while here now. Hopefully I'm not going too fast for you guys. I know this is all review for you, so maybe you'll just kind of get refreshed here, and hopefully you'll find this useful. So first step here is going to be to set it equal to 0. Then we're going to divide out any GCFs that we can find. We do have a GCF of 3 here, so I'm going to divide out that 3. And I get 3 times x squared minus 7x plus 10 equals 0. Divide both sides by 3. I'm just going to highlight this so I don't have to write it again. Divide both sides by 3, and 0 divided by 3 is 0. So that's kind of the nice thing about dividing out that GCF is you just make this a little easier to solve for. So what I'm looking for here now are going to be 2 values that multiply to give me 10 but add up to negative 7. So if your product is positive but your sum is negative, that means both those numbers have to be negative. Right? A negative times a negative is positive, and that's the only way we can add them up to make it a negative. So that's going to be negative 5 and negative 2 here. So we get x minus 5, x minus 2. Again, the order here is not important, but this is going to be how they factor out. And so now what I'm going to do is essentially set each one of these factors equal to 0, and I'm allowed to do that because of the zero product property. So x minus 5 equals 0, or x minus 2 equals 0. And kind of important to throw that or in there, just from like a, being technically correct here. It's a good idea to throw that in there. Now, if you just like use a comma or something, it's going to be okay, but you really want to know they could be this or that. Okay, so my solutions here are going to be x equals 5 or x equals 2. What happened there? Sometimes I press these buttons and I don't know what I'm doing. I'll say most of the time. Okay. Okay, so this takes a while to kind of get that in there. All right, so here we go. We got our solutions of 5 and 2. Now this one over here is set up for us to divide up front. So that's kind of nice. We don't have to do that. We don't have to find the GCF. The GCF found us. So we get x squared plus x equals 12 if we divide both sides by 2. And then we're going to subtract the 12 from both sides because we need it equal to 0. So we get x squared plus x minus 12. So we're looking for 2 numbers that multiply to give me negative 12. So if they multiply to give me a negative, that means one's positive, one's negative. So I need their product to be negative 12 and their sum to be positive 1. If you don't see a number for that x, the coefficient is assumed to be 1. So that's going to be minus 4 plus 3. And the only reason I'm kind of quick to come up with this is just practice. I'm not a genius or anything. It just takes a little bit. If you do these enough, you'll start to recognize patterns in the numbers. So negative 12 times 3 is negative 12, and then you add these. Oh, wait a minute. If I add these together, I get a negative 1. So I need to flip these signs. I need a positive 4 and a negative 3. Yeah, okay, now we're good. So 4 plus negative 3 is positive 1. A good thing I caught that. So after you write it down, just make sure you kind of look back and say and check, as you're going, like I just did there, because you might find out that you made a mistake somewhere. I make mistakes all the time. So hopefully not too many. Okay, so here we go. X plus 4 equals 0, and x minus 3 equals 0. So we get x equals negative 4 and x equals 3. Now, like I was saying before, there are other ways that you can solve quadratic equations. If you're pretty comfortable with, say, the quadratic formula, that's fine. Quadratic formula will get you there. Factoring doesn't always work. There are cases, there are quadratic equations that are solvable, but not through factoring, at least the way that we typically do it. So just know that you want to try to factor, but at the end of the day, if you can't, you can use quadratic formula. So that's pretty much it for today. Just wanted to do a refresher with you guys regarding solving linear equations and solving some factorable quadratics. Next time, we'll kind of get into some more nuts and bolts, reviewing just other random stuff that is going to be helpful throughout this year. But that's it for today. Y'all have a great day.